Hello. Thanks for coming in today. It is great to meet you. To get us started, why don't you just tell me a bit about your background and what drew you to the world of animation and VFX?
Thank you so much for having me. I am really excited to be here. I recently graduated with my degree in digital arts and animation. I have always been fascinated by the bridge between technical engineering and creative storytelling. For me, the magic is in the details, like how a character's skin folds or how light interacts with a cloud of smoke. During my studies, I spent a lot of time diving into the technical side of things, specifically rigging and simulation, because I love the challenge of making something digital feel like it has actual physical weight and presence in a scene. I do not have a long list of professional credits yet, but I have spent the last year pushing myself through several intensive academic projects and a few internships where I focused on the pipeline. From modeling to final render.
That enthusiasm is great to hear. Since you mentioned the technical side, let us dive right in. Let us start with the basics of character setup. From your perspective, what is the primary function of a rigging system?
The primary function of a rigging system is essentially to create a digital skeleton for a 3D model. The goal is to allow animators to control the model's movements efficiently. If you think about it, a 3D mesh is just a collection of vertices and polygons. Without a rig, animating a complex character would be an absolute nightmare, because you would have to manually move thousands of vertices for every single frame. The rigging system provides a framework of bones, joints, and controls that define how that model can bend, twist, or deform realistically. It transforms the model from a static sculpture into a puppet that an animator can actually perform with.
Right, it is all about creating that interface for the animator. Now, when you are actually building those rigs, you often deal with different types of kinematics. Could you describe the basic concept of inverse kinematics, or IK, and why we use it?
Sure. Inverse kinematics, or IK, is a method used to control the movement of a chain of connected objects, like an arm or a leg, by manipulating the endpoint. In a traditional forward kinematics setup, if you wanted a character to touch a table, you would have to rotate the shoulder, then the elbow, then the wrist until the hand hit the surface. With IK, you just move the end effector, which is the hand in this case, to the table's position, and the system automatically calculates the necessary rotations for the elbow and shoulder to make that happen. It makes the animation process much more intuitive and significantly faster, especially for things like walking or grabbing objects, where the endpoint needs to stay locked to a specific location. Space.
That is a solid explanation. Now let us talk about the transition from the rig to the mesh. How do you typically prepare a model for animation, and specifically, why is weight painting such a critical part of that process?
Preparing a model involves a few key stages to make sure everything runs smoothly once the animator takes over. First, I always start by checking the geometry. I look for non-manifold edges, overlapping vertices, or any weird topology that could cause pinching or glitches during deformation. Once the mesh is clean, I create the rig, which is that digital skeleton we talked about. But the real magic happens during weight painting. Weight painting is crucial because it defines exactly how much influence each bone has over the vertices of the mesh. If you just let the software automatically assign weights, you often get these jagged, robotic movements. By carefully painting the weights, I can ensure that when a character's elbow bends, the skin stretches and compresses naturally rather than just collapsing in on itself. It is all about distributing that influence so the deformations look organic and realistic.
Speaking of deformations, imagine you are reviewing a shot and you notice a character's hands keep clipping through objects during a performance. If you were the technical artist on that project, what potential rigging issues would you investigate to fix this?
Clipping is a common headache. First, I would look at the hand controls and the IK solvers to see if they lack proper collision detection or if there are missing constraints. Often, the rig simply does not account for the physical volume of the hand, allowing it to penetrate the geometry of the prop. I would also check the hierarchy in parenting. Sometimes the hand bones aren't properly influenced by the arm or the rest of the body, which can cause the hand to drift or move unnaturally. Then I would dive back into the skin weights. If the weights are poorly distributed, A simple wrist rotation might push the geometry of the hand further than the bone actually is, causing it to clip into a surface. Finally, I would see if the rig needs secondary or dynamic controls that could allow the animator to nudge the hand's position relative to the environment without breaking the main pose.
Let us shift gears toward animation principles. If you have a character whose movement feels stiff and lifeless, which principle would you use to improve the feeling of weight and fluidity?
I would definitely look toward squash and stretch. That is the go-to principle for removing stiffness. It gives characters a sense of flexibility and weight by exaggerating their shape during movement. For example, if a character jumps, they should squash down slightly as they load up their energy and then stretch out as they launch upward. This mimics how real-world materials deform under force. When you apply squash and stretch, the motion stops feeling like a rigid plastic toy and starts feeling like a living creature with muscle and mass. It adds a level of energy and dynamism that makes the animation feel much more natural.
That makes sense. Let us try a more complex scenario. You are animating a creature that needs to transition from a low, crouched state into a full-out sprint. Which animation principles would you focus on to make that transition believable?
That transition is all about the buildup and the release of energy. I would focus on four main things: anticipation, follow-through, squash and stretch, and timing. First, I would use anticipation. Before the creature sprints, there needs to be a slight shift backward or a deeper crouch to signal to the viewer that a big movement is coming. Then I would use squash and stretch during that initial launch to emphasize the power of the legs. Timing is also huge here. The crouch should be relatively slower, creating tension, while the transition into the sprint should accelerate smoothly and rapidly. Finally, I would implement follow-through. As the creature hits full speed, things like a tail, ears, or loose skin should continue to move slightly after the main body has shifted, which prevents the motion from looking abrupt or robotic.
I like that you mentioned the tail and secondary motions. Actually, that leads me to a more technical question. If you were tasked with simulating something very erratic, like a squirrel scampering around a park, what mathematical or procedural techniques would you employ to get that natural, unpredictable feel?
To get that kind of erratic movement, I would avoid manual keyframing for everything and instead use a blend of procedural techniques. I would start with Perlin noise or simplex noise to generate organic variations in the movement. This prevents the motion from looking repetitive or too perfectly looped. I would also use inverse kinematics to ensure the paws are planting correctly on uneven terrain. To add that twitchy quality squirrels have, I would implement a state machine or behavior tree. This would allow the creature to switch rapidly between states, like darting, stopping, and turning, based on environmental triggers. I would also add some physics-based elements, like a mass spring system for the tail, so it has a natural wobble and flick that reacts to the body's sudden changes in direction. Layering these procedural offsets with slight variations in timing creates that illusion of unpredictability.
Now let us talk about the darker side of rigging. What is the concept of null space in a rigging setup, and why is it something you want to avoid?
In the context of rigging, null space occurs when a joint or a control exists in the system, but has absolutely no influence over the deformation of the mesh. Essentially, it is a control that does nothing. This usually happens if the joint's transformations aren't connected to the skin weights, or if another joint's influence completely overrides it. You want to avoid this because it adds unnecessary complexity to the rig. When a rig is bloated with dead controls, it makes the file heavier, slows down the viewport, and more importantly, it confuses the animator. An animator might spend time tweaking a control only to realize it is not actually moving the character. A clean rig should be efficient, where every single joint and control serves a clear, purposeful role in the final deformation.
Let us move into some high-end technical territory. If you were designing a completely novel physics simulation system for a feature film, what core principles would govern its creation and stability?
That is a huge challenge. If I were building a system from scratch, the governing principles would be a balance of physical realism, artistic control, and computational stability. First, I would rely on conservation laws like energy and momentum to ensure that the simulation feels plausible to the human eye. To prevent the simulation from exploding or jittering, which happens a lot with complex solvers, I would focus on numerical stability and robust integration methods. Modularity would also be key. Artists cannot be expected to understand the underlying calculus, so I would build in artistic overrides that allow them to tweak the behavior without breaking the physical constraints of the system. Finally, because film production handles such massive amounts of data, the system would have to be optimized for parallel processing on GPUs to allow for faster previews while maintaining high fidelity for the final render.
Speaking of high-end simulations, let us talk about fluid dynamics. What are some of the biggest challenges associated with simulating interacting elements, like water splashing off a piece of metal?
The difficulty comes from the fact that you are dealing with two completely opposite material properties. Water is fluid, deformable, and governed by surface tension and viscosity, while metal is rigid and reflective. The simulation has to accurately handle the collision detection between those two surfaces and the transfer of energy during the impact. You have to calculate how the water breaks into droplets and ripples, which requires a huge amount of computational power. Beyond the physics, the rendering adds another layer of complexity. You have to handle the reflections of the metal in the water and the refractive properties of the splashes. High-resolution simulations with millions of particles are incredibly resource-intensive and slow, so finding the balance between a believable look and a manageable render time is always the biggest hurdle.
You have a good grasp of the physics. Let us pivot to hair and fur. What is the mathematical basis for simulating realistic hair growth or displacement, and what are the common pitfalls in that process?
Simulating hair usually relies on physics-based models from continuum mechanics and differential geometry. We treat each hair strand as a collection of elastic rods or curves. Mathematically, these are often represented as splines. We use things like the Frenet-Serret formulas to describe the geometry of the curve and partial differential equations to model the dynamics of how the hair bends and stretches under gravity or wind. One of the biggest pitfalls is numerical instability. Because hair is so thin and flexible, the equations can become stiff, leading to those weird jitters where the hair starts vibrating wildly. Another issue is collision handling. Preventing thousands of hairs from intersecting with each other or clipping through the character's skin without killing the render time is very difficult. It often requires complex smoothing techniques or additional constraints to maintain the volume of the hair.
Let us talk about the visual side of things for a moment. How does volumetric rendering differ from traditional surface rendering, and in what scenarios is it absolutely crucial?
Traditional surface rendering is all about the shell. It calculates how light hits the exterior geometry of an object using textures and shaders. It is perfect for a car or a building because those have defined surfaces. Volumetric rendering, however, simulates how light interacts with a three-dimensional volume of data. There is no distinct surface. Instead, the light scatters, absorbs, or emits as it passes through the volume. This is crucial for things like clouds, smoke, fog, or fire. If you used surface rendering for a cloud, it would look like a solid piece of carved foam. Volumetric rendering allows for the depth and translucency that make atmospheric effects look real. It is also used heavily in medical imaging, like CT scans, where you need to see through different densities of tissue.
Interesting. Now, when you are producing a final scene, you might have an explosion, a main character, and environmental effects all in one shot. How do you manage the performance budget and the artistic intent when combining so many complex elements?
The key there is prioritization. You have to decide what the audience is actually looking at. If the shot is a close-up of the character's face during an explosion, the facial microexpressions get the highest detail budget, while the distant debris can be simplified. I would use level of detail, or LOD, techniques to reduce the complexity of background elements. I would also optimize textures and shaders, perhaps using lower resolution maps for things that are blurred by motion or obscured by smoke. It is all about collaboration. I would work with the director to define what the hero element of the shot is, and then set strict polygon and texture limits for everything else. Using profiling software helps identify exactly where the bottlenecks are, so you can optimize the technical side without compromising the creative vision.
I want to go back to character rigs. You mentioned a layered approach earlier. If you had to structure a rig to handle both extreme performance, like high-intensity martial arts, and very subtle emotional micro-expressions at the same time, how would you do it?
I would definitely use a decoupled, layered system. For the broad, extreme movements, I would build a robust skeletal hierarchy using IK for the limbs, and perhaps a spline-based system for the spine to allow for those fluid, sweeping motions. This layer handles the physics and the big poses. Then I would add a secondary layer specifically for the face. This would be driven by a combination of blend shapes and a direct manipulation rig. I would use space switching so that the facial controls follow the head's movement perfectly, but can still be adjusted independently. To prevent the mesh from collapsing during extreme martial arts poses, I would implement corrective shapes, basically fix-it shapes that trigger when a joint reaches a certain angle. This way, the animator can push the body to the limit without the face or joints distorting, and then they can layer the subtle emotional twitches on top of that performance.
That is a very professional approach. Let us talk about a couple of quicker technical points. First, can you explain what shader compilation is and why it is so important during the rendering process?
Shader compilation is the process of taking shader code, which is written in high-level languages like GLSL or HLSL, and converting it into machine code that the GPU can actually execute. Since GPUs cannot read high-level code directly, this translation is essential. It is important because the compiled shader tells the GPU exactly how to calculate lighting, shadows, and textures for every pixel on the screen. If compilation fails or is done inefficiently, you get visual glitches or massive drops in frame rate. In real-time rendering, this is why you sometimes see compiling shaders loading screens in games. The system is optimizing the code for your specific hardware to ensure the render is as fast and smooth as possible.
Got it. And in a more general sense, what does a spline curve primarily control in 3D software?
A spline curve primarily controls the shape and flow of a smooth, continuous line. Instead of dealing with a series of straight segments, you use control points to influence the curvature. It is incredibly versatile. We use splines for modeling organic shapes, but they are also essential for animating motion paths, like a camera sweeping through a scene, or for defining the structure of hair and cables. It allows for a much more fluid and natural look than linear paths.
Now let us talk about texturing. Could you describe the difference in process between creating a procedural texture set and a hand-painted one?
Procedural textures are generated using algorithms and mathematical rules. Instead of painting a pixel, you are essentially setting parameters, like noise scale, frequency, and color ramps, to create a pattern. The big advantage here is scalability and iteration. If you decide the marble texture needs to be slightly more veined, you just change a slider rather than repainting the whole model. It is great for natural patterns like wood, stone, or clouds. Hand-painted textures, on the other hand, are created manually. An artist uses digital brushes to paint every detail, every smudge of dirt, and every highlight. This gives you total artistic control and a unique, stylized look that proceduralism struggled to mimic. However, it is much more time-consuming and harder to change once the texture is finalized.
Last question on lighting. Which type of lighting is generally used to separate a subject from its background, and how does it work?
That would be rim lighting. You place the light source behind or slightly to the side of the subject. This creates a thin, bright outline of light along the edges of the character or object. It is an incredibly effective way to define the subject's silhouette and prevent them from blending into a dark or busy background. It adds a sense of depth and three-dimensionality to the scene, making the subject pop and feel like they are actually occupying a physical space.
Finally, let us touch on a practical problem. If you are working on a project and the character's lip syncing is just not landing right, but you do not have the time to redo the entire technical setup, what are two non-technical methods you might suggest to improve it?
If I cannot change the technical rig or the audio, I would focus on timing and exaggeration. First, I would adjust the timing of the animation to better match the natural cadence of the audio. Sometimes just shifting a mouth shape a couple of frames forward or backward can make a huge difference in how the brain perceives the sync. Second, I would exaggerate the mouth shapes. In animation, the perfect anatomical movement often looks stiff or unreadable on screen. By slightly overextending the mouth shapes for key phonetic sounds, the movements become more readable to the audience, which makes the sync feel more believable, even if it is not mathematically perfect.
That is a very practical way to look at it. Well, you have a very strong handle on the fundamentals, and your ability to explain the technical side in a way that relates to the artistic output is impressive. We have covered a lot of ground today. Do you have any questions for us?
I do. I was wondering, for a junior role in your pipeline, how much cross-collaboration is there between the rigging and animation teams? I really enjoy the technical side, but I love seeing how the animators actually use the tools I build. I would love to know if there are opportunities to iterate on rigs based on the animators' feedback during production.
That is a great question. We actually encourage a very tight feedback loop. Our riggers and animators work side by side, and we often do rig stress tests where the animators try to break the rig in the most extreme ways possible so the riggers can fix those issues before the shot goes to final. We believe the best rigs are the ones that are refined through actual use.
That sounds exactly like the kind of environment I am looking for. Thank you for the insight.
It was a pleasure talking with you. We will be in touch soon regarding the next steps. Have a great day.
Thank you. You too.